This is Rosen, Discrete Mathematics and its Applications, section 8.5. We will learn a principle of counting called inclusion-exclusion for counting up the cardinalities of multiple sets and their relationships under union and intersection. And we'll do that first bullet in this video, and we'll do a separate video for an example. All right, so earlier in this text in chapter 2, we covered the concept of counting up the cardinality of the union of two sets as the sum of the cardinalities minus the intersection. We have to subtract off a cardinality intersection because we have double counted anything in the intersection by just adding up the cardinalities of A and B, and we'll come up with a general formula for this for any number of sets. Here's an example with two sets. I've got computer science majors and math majors, 25 computer science, 13 math, but I have some that are double majors. So how many are in my class? The number in class is the cardinality of the union of those two sets. So if I want to get that cardinality, I just add up cardinality of the component sets, subtract off the cardinality intersection to get 30 people in the class. All right, and there's the Venn diagram representation of it. Notice that we would have double counted the people in that intersection if we just counted the cardinalities of A and B. What about three sets? Well, it turns out for three sets, if I want the cardinality of the union of three sets, I add up the cardinalities of the individual sets, I subtract off all the cardinalities of the two-way interactions, then I add back in the cardinality of the three-way interaction. Why does that work? Let's keep track of what we've overcounted and undercounted. Here I have a Venn diagram for all three of my sets, and by adding up the cardinalities of the individual sets, you can see that I've double counted everything that is solely in a two-way interaction, and I've actually triple counted those elements in the three-way interaction. So let's first subtract off, copy the cardinalities of the two-way interactions. And once I do that, my 2 goes to a 1 in every case. But notice that since I've subtracted it 3 times, my 3 counting of the triple intersection has gone to 0, so I need to add a copy of it back in, or a cardinality back in, to make sure I only have a 1 and counting everything only once. All right, and one pattern here is that whenever I'm calculating the union of a set, for odd numbers of intersections, I'm adding the cardinalities, and for even numbers of intersections, I'm subtracting the cardinalities. Here, odd, I'm adding, even, I'm subtracting. Well, that's what I'm doing in the union. Okay, so let's look at another example. Here I have students taking Spanish and French and Russian, 1232 taking Spanish, 879 taking French, and 114 taking Russian. And I already have the cardinality of the union. So in this situation, we want to know how many are taking all three languages. That would be the cardinality of the intersection. So that using our formula from before, there's 8 terms. If I have any 7 of those terms, I can get the 8th term. I do have intersection cardinalities, 103 in Spanish and French, 23 in Spanish and Russian, and 14 in French and Russian. All right, let's populate our formula. Here I have it expressed in terms of cardinalities. Cardinality Spanish, cardinality French, cardinality Russian students, two-way interactions. And I have my union that was given to us, but I want to look for the intersection. So here's my inclusion-exclusion equation. I know everything but that. Let's calculate that to be 7 are in all 3 languages. Truly gluttons for punishment. And here's another diagram that shows each of those sets. Here's the triple intersection, the double intersection in all cases, and the single sets. So this is nice for 3 sets. You can see all possible interactions, 2-way and 3-way, and no-way interactions. But in general, that's difficult to do. From 4 or more sets, you cannot, with a planar diagram, get all the intersections. So the Venn diagram starts to fail us trying to exhibit all of these intersections. You can try it, but please don't do it on a test. What can we do to handle 4 or more sets that we want to try to find the cardinality of the union? Well, we have a formula for that. It's called the principle of inclusion-exclusion. Let's say I want to find the cardinality of the union of n sets. Well, we will start by adding up the cardinalities of all those sets. And then notice that negative sign there, we'll subtract off all the cardinalities of the 2-way interactions. And there's a plus here. We're going to add the cardinalities of the 3-way interactions. And in general, if there's an even number, we subtract. And if there's an odd number, we add. And then that last item, if n is, this is the all-way interaction. And if n is even, then n plus 1 is odd, and I subtract. If n is odd, then n plus 1 is even, and I add. So one question is, how many of these 2-way interactions are there? How many of these 3-way interactions are there? I'm glad you asked, and here's the report. They are the number of combinations of n things taken m at a time. We have a formula for that. N factorial over m factorial and n minus m factorial. So keep in mind that you may have more interactions than you're thinking about. So use this formula to make sure you know how many there are. And in a separate video, we'll do another example.